In Chapter 10, we embark on the process of techniques of integration. We will learn a few very useful techniques. First one we're going to start with is basically anti-chain rule. Every integration technique is somehow grounded in the corresponding differentiation technique, but the backward process is usually a little bit more complicated. So in order to understand it best, let's first go through the differentiation as we have seen in Calculus 1, and then think about how to reverse it. So if I start with the function x squared, that's my y, then dy by dx, and I'm going to use this notation here, is going to be equal to 2x. Now, what I can do is think about how is this a ratio that I can use to my advantage. If I can draw a quick little graph here of what a general function is and what this dy by dx represents, then let's say this is my function f of x, and what I actually have is the dy by dx represents the rise over run, of course, the slope of the tangent line, and it does approach the tangent line as the dx value gets infinitely small. So as I get closer and closer in terms of these 2 points converging towards each other, my what is called secant line becomes in fact a line tangent to the graph. But here what I have is dy by dx, and what I can say is that the slope of the tangent is actually equal to the value of the derivative, which we also denote by dy by dx, and that is my rise over run, which means that treating dy by dx as a ratio can actually be utilized and be useful. You just got to be careful in realizing that generally this is a ratio only as a limit when the dx value gets infinitely small. But using this idea and thinking about this as a ratio, what I can do more or less is multiply both sides by dx and therefore have it moved to the right hand side. So in that scenario, dy, my change in y, is equal to 2x times the change in x. So 2x times the change in x. For any fixed value of x, we can then compute this dy. What happens if the function gets more complicated? So here, recall the chain rule. The chain rule tells you to bring the power down, reduce it by 1, and then take the derivative of the inside. So in this case, times 5. So here too, I can again think of this as the rise over run and multiply everything by dx in order to get my rise here only in terms of my derivative and the value for the run. So combining the two numbers together, 3 times 5 is 15. So I'm going to have 15 5x plus 1 squared times dx. And this will, of course, hold for any function that I choose to take a derivative of. The derivative of sine 2x, again, the chain rule. So first I take the derivative of the outside, which is the trig function. So the derivative of sine is cosine of the same inside, times the derivative of the inside, so 2. And again, rewriting in terms of dy only, I can have 2 cosine of 2x times dx. Notice too that we can actually skip this middle step with enough practice and go directly from the first line to the third one. If I just think of taking a derivative and carrying through the dy, kind of like implicit differentiation, and dx every time I take a derivative of x, then I can skip this middle line and go directly to here. Same thing here. The dy is going to be the chain rule applied, followed by dx. Next, let's see how we can use this line and this rewriting of what dy by dx can actually be to compute some integrals. So if we don't think of it as an integral first and we just consider the function, if I were to take a derivative of it, I would have to invoke the chain rule because the inside here isn't just x. And that's the case for all of the functions on this slide. Now, if this function is an antiderivative, or if I am to take an antiderivative of it, that means that I have to think of this as a derivative of some other function. But again, because the inside is non-trivial, that means that the function the differentiation and therefore anti-differentiation process had to involve the chain rule. Now, there are a number of different ways to actually do what we're going to do, and which is so-called substitution. And I'm going to show you two different ways, but let's go through the process one way at a time. The first thing you can do is substitute the inside with a variable alone. So here, it would be really nice if the inside was just its own function. So what I'm going to do is call this x plus 1 u. U is the normal, I'm not really sure why it's actually called u, but this is the normal variable used in substitution. You can, of course, make it anything at all, but u is the letter that is generally picked. Now, the reason it's called the substitution box is because I'm actually going to create a box where I write all of the information I'm going to use and then substitute all of that information back into my integral. Now, notice that if I sub in this for u, then my problem is the remaining dx. If I'm going to rewrite the entire integral in terms of this new function u, then the differential also has to be in terms of u. So what I'm going to do here is take a look at this expression and take a derivative of it one step at a time. So derivative of u is du by dx. The derivative of x is just 1, the derivative of 1 is just 0. So on the right-hand side, I'm simply going to get a 1. And then I'm actually going to extend my box here. What we are next going to do is notice that I don't care for the expression du by dx because that's not what's in my integral. I care about dx alone. So here is where we're going to take this expression and treat the left-hand side as the ratio, as we've just talked about on the previous slide, and rewrite it as just du and just dx. I'm going to multiply both sides by dx. In this case, the expression comes out being very simple. Du is equal to dx. And so what I actually can note is that this dx is the same as du as per my calculations here. So what am I now able to do is rewrite this entire integral in terms of u and u alone. So this is now the integral of u squared du. Now, once I have that and I'm consistent with my variables throughout, can I integrate this? Well, sure. Now I can apply the power rule because my variable is simply itself. The du indicates that this is in fact the variable I'm working with. So the antiderivative here is a straightforward u cubed over 3 plus a constant. Now, if my original integral was in terms of x, then my answer should be in terms of x also. So I am going to resubstitute what u was in terms of x back in. I have u cubed, which really means I have x plus 1 cubed over 3 plus a constant. Remember that one nice thing about integration is that you can always check it by differentiation. If I take a derivative of this, will I get x plus 1 squared back? Well, let's see. If I take a derivative of this, 3 comes down to the front and the power gets reduced by 1. 3's will cancel. The derivative of constant is just 0, so I will in fact get exactly x plus 1 squared, which is what I started with here. Now let's see if we can use this process again with an example that is very similar, just a little bit more complicated. So here I have something squared dx. And again, it would be really nice if this something was just its own function. So let me call this u. And again, now I'm going to have to figure out how to rewrite dx in terms of u and du. So I'm going to introduce my substitution box. I'm going to note that I made u 5x plus 1, and then I'm going to take a derivative of it. So du by dx, the derivative of u with respect to x is equal to 5. The derivative of 5x is just 5. The derivative of 1 is 0, so just 5. And again, while this is a nice enough expression, what I actually need is dx by itself. So I'm going to solve this for dx. From here, you can cross multiply. You will see that dx is equal to du divided by 5. Now, what does that mean in terms of my integral? Well, let's plug everything else back in. So first of all, dx is du over 5. So I can even write this down here, du over 5. And then what I have is u squared times du over 5. U squared times du over 5. Okay? So again, I would like to write everything inside this integral all in terms of u. I get to pick what my u is, and then I get to calculate dx in terms of du. Once I've managed to do that, I sub in the new expression for u, x's, and dx in order to get the next integral all in terms of u. If your next integral is not all in terms of u, that means that the substitution failed. You have to be able to get rid of x's entirely at this stage. Now remember that if I have a constant, I can simply take it outside of the integral and then integrate what is remaining. So here I'm going to take out 1/5, and in the integral I'm going to have left u squared du. Now I'm actually at the exact same point as I was in the last example, so I can simply note that the antiderivative of u squared is u cubed over 3 plus a constant. And then, as before, if my original integral was in terms of x, my answer should be in terms of x also. So I'm going to resubstitute the expression for u back into my answer. So here I'm going to have 1/5 times 5x plus 1 cubed over 3 plus a constant. And once again, you can check this answer using differentiation. If I take a derivative of this now, will I have 5x plus 1 all squared? I leave this up to you to confirm that this is in fact correct. Let's try this next one. It looks very complicated, but it really isn't. And this will also show us another way to spot when a substitution is an appropriate technique. What I have here is 2x times the square root of x squared plus 1. Now, square roots are famous for being hard to simplify. So as the first clue, you can try to see if it will work out if we rename whatever is under square root to be its own function. So what if I call this u? What would then the substitution tell me? So I'm going to have that u is x squared plus 1. And I also note that, for example, in this first case here, I can basically kind of skip the first step once I do enough of these exercises, just to see. So for example, here, instead of going through these two steps, I could have also done that du is equal to 5 dx right away, taking the derivatives of each of my variables separately. So here, if I have that u is x squared plus 1, then du is 2x dx. Okay, if you're not comfortable with this, that's totally fine. Again, you'll get more comfortable with this once you do like 20 of these. So if this is too much of a step to skip for now, please do go through the same process we've done before. So on the left-hand side, you will always have du by dx, and on the right-hand side, you will just get the derivative of what you have there, and then you'll go through the motion of multiplying everything by dx. Now, what is noticeable here, though, is I don't actually have to solve for dx to replug it back in, because very conveniently, 2x times dx is exactly what I have left in the integral apart from my square root. So these two portions, this 2x and this dx, are exactly what forms du as per my derived formula. So you can always solve for dx and then plug it into dx exactly, and you should try to do it in this case as well. Or if it's really working out well, then you should be able to spot du as a part of the integral as written. I generally recommend to solve for it because that's a foolproof technique. Things that work out this nicely will not happen too often. But in this case then, what we have all together is I have square root of u, and the rest of my integral becomes du. So square root of u du. Now square root is actually power of 1/2, And once I have that, I note that I can easily anti-differentiate this. I add 1 to the power, so 3/2, and I divide by that number plus a constant. And then once again, I would like to bring it back to my original variable, which was x, and I go back through the substitution box, noting that u was equal to x squared plus 1. So I have x squared plus 1 to power 3/2 over 3/2 plus a constant. Substitution is it's the first technique that we're considering. It's also one of the simplest ones, but it's probably one of the hardest ones to really grasp because it is such a technical thing to do. So this will simply take practice. Trust me, at the end of it, substitution will be fairly straightforward, but at the end of it, meaning 20 more substitution examples from now. So let's see what we can do in terms of practice. I strongly encourage you to pause the video here and try this for yourself and then come back to see the actual solutions. Generally, the hardest step in the substitution is figuring out what to substitute for. So what is going to be your u? So once you see the first step, the rest of it is fairly straightforward calculations. But for now, this is the step to practice. Pause the video. Think about what u is in each of these examples, or what would you like u to be, and then come back to take a look at what I have. Okay, so here we have x cubed cosine of x to the 4th plus 2. So cosine has this really bulky inside, and this is probably a good first attempt at making the u equal to x to the 4th plus 2. Let's see if that's going to work out. We will know if it does or not in the next step after the substitution. It does work, or it means working out means that my next integral will be able to be written fully in terms of u, maybe to some powers, maybe with some coefficients, but containing u and u alone. No x's. If the next integral still contains x's, that means that your substitution did not work out and you need to think of something else to substitute for. Let's see if we start with u equals x to the 4th plus 2. Then my next step is to compute du, which in this case will be 4x cubed dx. And this is already pretty good start. Because what I notice then is I can have the integral. I have x cubed here. I'm going to rewrite it. And if it doesn't cancel within a step, then I'm in trouble. I have x cubed times cosine of u times dx. From this expression, we can solve for dx. So from here, I have that dx is equal to du over 4x cubed. And that is a thing that I can substitute for du. Okay, so again, compare the beginning integral to this one now. What I have before was x cubed times cosine of a thing times dx. And I've now replaced that thing with u and dx with the expression for it in terms of du. Now, it is clear that everything is going to work out because this x cubed and this x cubed canceled. So my next integral is going to be cosine of u du, and I can take my 1/4 out of the integral because it's just a constant. Okay, I'm going to leave the rest of the calculations to you because from now on it's really straightforward. You take the antiderivative of cosine of u, you multiply this by 1/4, and then you rewrite the resulting antiderivative in terms of your original variable x. Let's take a look at this next integral. What should I make u? Well, here it's kind of the same problem as on the last slide, the last example, where the square root has something in the inside and we cannot break it apart. So we will try to make the inside of that entire square root to be our u. And then what is it gonna be in terms of du? Well, I'm gonna have that du is 8x dx, and I can already see that this has good promise because x dx is exactly what appears in my integral. So I can replace x dx, which is what's there, by du over 8. So this is looking promising because now I'm going to have du over 8 over square root of u, and I'm going to let you carry out the simplifications to make sure that it works out. This next integral is one of the first few that we're going to look at in terms of trigonometric functions. Tangent is not something that we know antiderivative of very easily off the top of our hand, but sine and cosine are much more familiar trigonometric functions to deal with. So why don't we rewrite this integral first of all in terms of sine and cosine, and then see if there's anything you can do. So what we can try here is a substitution u equals cosine x, or a substitution u equals sine x. I suggest you try both and see which one works out and which one does not. Now they might both work out or they might both not work out, but you will see in the case when it doesn't work out, if there is one, what exactly goes wrong and what does going wrong really look like. So please do both of these substitutions to really carry through. Now, in the most generality, this is how the substitution is actually written down. You might remember the left-hand side as the expression for the chain rule, right? So let's remember that the chain rule states that if I take a derivative of f of g of x, then I take derivative of the outside function first, followed by the derivative of the inside function. And that is exactly what I see here inside the integral. Notice the typo. Okay? So what this is saying is, in order for me to have gotten this as an answer, what did I have to take a derivative of? I had to take a derivative of f of g of x, which will be much easier to look at, much easier on the eye, if the inside was just simply called u. Okay? So the substitution is really an anti-chain rule. And as I've already mentioned, there are two small but important nuances that you should keep in mind when doing the substitution. So the first one is the fact that after the substitution, integral should be in terms of one variable only. Now, as we've noticed on the previous slide, it might take another step to actually get rid of x's, but if in that step it's not clear how to do so, then the substitution has failed. If you cannot consolidate the entire integral to contain u only, then the substitution failed. And the second important nuance in all of these substitution examples is that you should always go back to the original variable. So if the integral was given in terms of x, then you need to go back to the original variable x. And that is because your choice of substitution might be different than another person's choice of substitution. If all I have is the integral at the beginning that is given in terms of x, then my answer should correspond to that. Let's take a look at two more examples where a simple substitution will lead to quite impressive results in terms of the actual integration. So this first one here, x square root of x plus 1. We've already seen enough examples with square roots to notice that the substitution u equals x plus 1 is probably the one we're after. We are going to replace whatever is under the square root with u. Now, carrying through the substitution here, I notice that du is equal to dx, which means that this is now going to be simply du. So here then, what am I going to have? I have this x in the front. I'm going to leave it for now. I have square root of u, and then I have dx, which is the same as du. So now I am faced with the problem of having this x out here. Can I rewrite this x in terms of u? Is it possible? Well, let's take a look back into our substitution box. How can I solve this for x? Well, it's pretty clear that from here x is equal to u minus 1, right? So I can replace it with that in this integral here, which will then result in my integral being fully in terms of u. Now that means that my substitution didn't fail, but did I make it better? Is the integral that I have now better than the integral I had originally? Well, on first sight, it doesn't even seem like I've made much progress, really. I still have a square root, I have a bracket in front of it. Here, it just seems like the two things were flipped around with the negative sign. But this integral is actually much better. See, this first integral, there's nothing I could do to simplify this. You cannot break apart a square root over the sum, and so I'm stuck with this as is. This integral, however, I can simplify by opening up the brackets. So let's do just that. If I open up the brackets, what am I going to get? I will have integral of u square root u minus square root u all du. And this is really great news because I can rewrite both of these pieces as powers of u. The first one is u to power 1 and then u to power 1/2. So altogether u to power 3/2 minus u to power 1/2. And now I can simply apply the power rule in order to find antiderivatives and then return to my original variable x. So I'm going to leave the last few steps up to you. With the trigonometric integrals, this is one of the examples we're going to do now. We will come back to, for a whole lecture, talk about integrals that involve trigonometric functions, but this is just a sneak peek, so to say. What I can do here is note that I can try to substitute for sine or can try to substitute for cosine. And one might work, one might not. So again, I strongly recommend that you pause here and you try both. Try u equals cosine of x and try u equals sine of x as your substitution. See which one of these cases will result in what. Pause now, come back in a second. Okay, so let's say that you are a good student and you actually did pause as instructed. And what are we going to get in terms of the substitution here? U equals sine x will actually work out. And it will work out really nicely and really quickly because the derivative of sine of x is cosine x dx. So what I notice in my integral right away is that I have this is, if sine x is u, then this is u squared. And then cosine x dx is actually my du. So my integral becomes really simple right away. U squared du. I can integrate this instantly with the power rule, and then I can replace u with my original variable, which is sine x, and get my answer right away. Again, you can double check to make sure that the derivative of this is in fact what I see in the middle here. And it's really instructive to try the substitution u equals cosine of x just to see why exactly it doesn't really work out and is not helpful. Please take a look at practice examples, exercises on WebWork for substitution. As I've mentioned, this material takes quite a bit of practice to do, but it will get a lot better with practice.